So we need to get pure copper on its own. So what we do is we will, this won't work, let's just do this. So what we can do is first of all, what does the word electrolysis mean? Electrolysis means splitting something in two. Okay, so the word electro means electricity, and the word lysis means splitting. So that's literally what electrolysis is, using electricity to split something up, like it says there. So, for electrolysis, we need two terminals, and you guys know all about this from the controlled assessment. The positive one is called the anode, and the negative one is called the cathode. And electrolysis needs to be done in solution so the atoms can move. You remember the blue solution, which was copper sulfate, and that blue solution is called the electrolyte. Okay, now the electrolyte enables electricity to be passed through it. It's got to be able to conduct electricity, and so all the copper atoms can come off one anode, which is coming off the anode and joining onto the cathode. Now, I'm not going to spend too much time going over this because we really are experts at this because of the controlled assessment. So with the copper sulfate, this is the anode. Anode gets smaller like that. The cathode, all the atoms from the copper are going to join onto the cathode, and the cathode gets heavier. And what happens right at the bottom? All the anode sludge, so all the impurities will sink towards the bottom part of there, and they will gather. Okay, so this is electrolysis. You've got the power supply, which is always DC, which is direct electricity. You don't want AC, because it'll just be going in two directions. And that is that. Okay, so literally, I've just skipped past through this because we've done so much on it already. Okay, you need to know all that. I'm just going to go through this and solve it. So the electrolyte is the copper sulfate, the cathode, which is a pure copper, and the copper that you want to recycle, like a copper boiler, is where you'd put this, the impure copper, and all the atoms from the impure copper will join onto the cathode, and the cathode will get a lot bigger. Okay? Yes. This is another drawing. So tell me something about rusting. You can see rusting over here happening. And so rusting and corrosion is what we want to look at. What is rusting? Rusting is the oxidation of iron. Oxidation means reacting with oxygen, so that's literally what happens. What metals rust? Well, iron and steel rust. Okay, now what conditions are needed for rusting to take place? And what you need is oxygen and water. Okay, so if you've got both of those present, you are going to get rusting, and that only happens with iron and steel. How do you stop rusting? Okay, what you want to do is you want to stop the oxygen and the water getting to it, so we can paint it, or we can covering it up with oil. Okay, do other metals rust? No. Only iron and steel rust, because steel obviously contains iron. But other metals do not rust, but they become duller when they react with oxygen. Okay, we call this corrosion. Now that is copper, and it is corroded. Okay, not rusted. Only iron can rust. It is corroded. Okay, so rusting is a chemical reaction between oxygen, iron, and water. And when it rusts, what happens is it makes hydrated, which means reacted with water, iron 3 oxide. Okay, and put it in a word equation. Iron plus oxygen plus water gives you hydrated iron 3 oxide. We know about word equations because we've done them, and that is essentially what is made. So you may see this question, and it comes up all the time. I remember doing this when I did my GCSE exams all that time ago. And how does this prove what conditions are needed for rusting? Well, if we've just put water and oxygen in it, okay, it's getting the two things. It's getting water and it's getting oxygen. You can see the rusting present. This has got a drying agent, so no water can get to it, but oxygen can get to it, no rusting. This one, we've put boiled water, we boil it to get rid of all the oxygen, but it does have just water present, and there's no rusting. Whereas you look at this test tube over here, this has got air and water, so you get rusting, but salt makes it happen a lot quicker. Yeah, so that's why when you go over to the seaside, you're going to get a lot of rusty cars, because salt speeds it up, and you can see this ship, which has become grounded. And it's rusting really quickly because of all the salt from the seawater. Okay, so salt speeds up rusting, but acid rain also speeds it up. Okay, so in the city, there's a bit of a double whammy, isn't it? Yeah. Now, thing you need to know about aluminium is aluminium does not corrode. Okay, aluminium does not corrode. Why? Because when you get aluminium, it reacts with oxygen really quickly, and you get a layer of aluminium oxide built up. Okay, now the aluminium oxide what it does is it provides like a protective barrier, and it stops oxygen from getting to it. Okay, any more oxygen, and it also stops water getting to it, and so no more further corrosion. So why doesn't iron oxide form a layer like aluminium oxide? Okay, well, the thing about aluminium oxide, okay, or rust, okay, it doesn't form a layer, but it forms flakes instead. And these flakes keep flaking off. Everyone's seen a little bit of rust, and you rub rust, and all the rust comes off, and so it exposes new iron all the time. That is aluminium oxide, but this is rust, and you can see how it can just be flaked off, and exposing more and more iron, so the rusting will keep continuing. Okay, ignore this little bit because my part 2, I actually stopped it after half an hour. Okay, so the harbour process. You can see that the world's population is increasing. All those years ago, suddenly after 1800, the world population, can you remember what this was called when it rockets up? Beginning with E, exponential growth, where the birth rate is higher than the death rate. Okay, with that, all those people, they're going to be starving, like these people over here. Okay, so what has a cow manure got to do with it? Well, cow manure contains fixed nitrogen. Okay, and we need fixed nitrogen. And we can get fixed nitrogen from cow manure, but there's only so much manure that we can go from it. So, why is manure so important? What do we get from it? We get fixed nitrogen. And as we know, that 78% of the air is nitrogen, so why can't plants take it from that? Because nitrogen is, as we say, unreactive. So plants can't absorb it just from the air. Nitrogen needs to be fixed. Okay, right. We're going to skip this, but I asked you guys during the lesson to write one paragraph about world population, famine, protein, and manure. And as you know, that the nitrogen is not fixed, but it is fixed in crops. And so when animals eat the plants, which has got fixed nitrogen in it, they produce manure, and the manure can be put onto the fields, and it provides fixed nitrogen for new plants to grow. Nitrogen is needed to make protein. Okay, how is nitrogen found in the soil? It is found as nitrates. Yeah? Okay, now, this man over here, a bit of a mixed bag, this dude. He was an amazing chemist, and he gave us fixed nitrogen, but he was also the godfather of war. Okay, we'll talk more about that in a second. So Fritz Haber found a way of fixing nitrogen. He found a way of getting nitrogen to fix with hydrogen to make ammonia, which is NH3. Okay, now today millions of tons of ammonia are made each year to make fertilizer to feed the world's growing population. Should put apostrophe in there. Okay, he won the Ballon d'Or for science in 1980. We call it the Nobel Prize, just for you football fanatics out there. So he was the godfather of war. So he actually found a way of making all these poisonous chemicals in World War II, and this is one of the famous pictures of him being likened to the devil. So the Haber process. Haber process involves reacting hydrogen and nitrogen together. Do you think this is easy? No, because nitrogen is unreactive. So nitrogen atoms and hydrogen atoms are not easily joined up together. Okay, but he found a way that he can join the gases together. He could get nitrogen and hydrogen to react together if he used high pressure, and if he used high temperature, and if he used an iron catalyst. Okay, problems. Now, the problem is the reaction is reversible. I think I said irreversible. I meant reversible. That's what the arrow means. It goes in the forward direction and it goes in the backwards direction. So you may get a picture of this and I might ask you what this means. It means reversible. That means that the nitrogen and hydrogen, as soon as we put all the work to put them together, they come apart again. Not good. It's a reversible reaction, and that's the symbol. Okay, what is the balance formula for it? You need to know it. Okay, and that is N2 plus 3 H2, because they're the H2s, and it makes 2 NH3. Okay, have I got that written down anywhere? I haven't. Okay, shall I put it in? I will do. Okay, I'm just going to use the pen to be able to do it. Okay, with my messy writing. So this is N. God, this looks terrible. So this is N2. You need to know this formula, guys. Plus 3 H2, and you've got the forward arrow. This is terrible. You've got the backwards arrow, and you've got 2, because there's 2 of them, NH. Oh God, this is terrible. H3. before you make fun of this, it's incredibly difficult to do this with a pen. And that is the balanced formula for it. So the forward reaction is nitrogen plus hydrogen gives you ammonia. The backwards reaction is that the ammonia will turn back into nitrogen and hydrogen. Okay, now this is the way how we get all of this to react. You remember seeing this. So you get the nitrogen and the hydrogen, and you push them together. So this creates the high pressure, which is a compressor. Okay, and so this will provide the pressure, and then it'll go the nitrogen, hydrogen, and the pressure will go into this big massive reaction vessel, which is at 450 degrees. These are the trays of iron catalyst, and the ammonia with some nitrogen and hydrogen will go into the liquefier. Liquefier is very, very cold, and it will turn the gas ammonia into liquid ammonia. Okay, but all the unreacted nitrogen, hydrogen, yeah, will go back round. We recycle it. Okay, and it'll go back round to this pressure, and as we keep pumping in more hydrogen, nitrogen into it, and it will keep going around because it's a continuous process. It means it never shuts down. It just keeps going round and round and round. Okay, guys, if I were you, I'd just rewind my explanation of this because it's really, really quite important. Okay, so the best conditions. We need to make as much ammonia as possible. So we can do this by changing two things: temperature, pressure, and, well, we're always going to keep the iron catalyst, but increasing the temperature makes the atoms move quicker and collide more. Increasing pressure, which means that they squeeze them together. So that's what we do. We increase the temperature so the atoms of nitrogen and hydrogen move faster, so they're more likely to collide and react, but we also increase the pressure, which pushes them together. Okay, now, so what conditions would you use? This looks at yields. So what are the best conditions? These are all the pressures over here, okay, and this is all the different temperatures, and this is all the percentage yields. If we got 100%, which is not possible, we would get all of the nitrogen and hydrogen reacting together to make a really, really high amount. All the nitrogen and hydrogen would make ammonia. So for that, the highest, what would give the highest yield? Well, we would use 400 pressure, and we'd use 100 degrees, wouldn't we? That would give the highest yield, yeah? So that would be the highest yield, but we don't pick that, okay? Even though it gives the highest yield. Why? Because it actually gives us the highest yield, but really, really slow reaction. It's really, really slow. So what we actually use, did you pick 400 and 100 degrees? We did. We picked 100 degrees and 400 pressures to give us 99% yield, but that is not that gives us the best yield, but we don't use that. Instead, we use 200 atmospheres and 450 degrees. So 200 atmospheres, okay, so we use that, and 450 degrees, which is in between here. So it gives us a yield between 39 and 30, which is around about 34-35% yield. Why? Because that reaction happens the quickest, okay, but it doesn't give us a maximum amount. But because it doesn't only gives us about 35% yield, it just, all the nitrogen and hydrogen left over, yeah, would go back round and back into the reaction vessel. Yeah, that's why it says 450 degrees and 200 pressure coming from this. Okay, so I've gone through this pretty quickly, and as I suggested earlier, you should go through this again. So those conditions give a poor yield, but the reaction happens quicker. That way they can make the product quicker, and they just recycle the gases through the reaction vessel again. So the cost of the fertilizer. Now, you see that the price of the fertilizer, yeah, including VAT, is £23.10. That's a lot, isn't it? Considering that they're just getting gases together, and so you're paying all that money for a fertilizer for all the gases. Well, the reason being is, why is it so much? Well, because they've got costs. They've got outlays that they need to pay. So isn't fertilizer made from air? Yes, it is. How can it cost so much? Because the basic cost of ammonia production include, number one, these are all things that you need to know what they're paying for to make the vessel go together, the actual building of the plant. So the cost of building the place is going to cost a lot of money, and you need pipes that are really thick steel. Why? Because it's under a lot of pressure. That's why you need really, really thick pipes, because 200 atmospheres of pressure have to pass through them, and if you use thin pipes, which is cheaper, the pipes will burst. That's no good. Nobody wants that. You have to pay for the cost of reactants. You thought gases were free, right? No. The hydrogen is made from cracking crude oil, okay? And the nitrogen, even though it's 78% of the air is nitrogen, okay, it still needs to be compressed, and we need to get pure, we need to get rid of the oxygen from it. So we need to actually clean it. We need to remove all the 0.035% of carbon dioxide. And it needs to be dried as well, taking all the water moisture out of it. Okay, you need to pay, people don't work for free, so you need to pay their costs, and you need to pay for energy costs. We need to heat them up to 450 degrees, people, all day long, and that will cost you money. And so you have to pay for that. So those are all the main things that we have to pay for. We have to pay for building the plant in the first place. We have to pay for the cost of the gases, which is the hydrogen and the nitrogen. The nice people over at the fractional distillation place aren't going to give you that hydrogen for free, you know. And the nitrogen still has to be purified. You need to pay for people to work there. You need to pay for the 450 degrees that it costs to put it in there in the first place. And you need to reduce the pollution costs, because when you're heating up all of that to 450 degrees, that's going to be making a lot of carbon dioxide. So you have to pay money to get the pollution cleaned up as well. Otherwise, you get a fine. Okay, so even though fertilizer costs money because it comes from air, you need to know why it costs so much. And all of those 5 points explain it. Go back and look at the 5 points, guys. Okay, so when we've made this amazing ammonia, what do we do with it? Well, first of all, the most obvious thing is that we make fertilizer. Second thing is we make household cleaner. And there you go. That is household cleaner right there. Okay, and that was the Haber process. Yeah. Okay, acids and alkali. I'm going through this quickly, I know, but let's try and get through it. Okay, acids and alkaline. How many times have you heard the word acid and alkali? Loads. What do they mean? Something can be acidic or something can be alkali. But how are they made? Water splits. Okay, that's right. Water does split. Okay, and when water splits, because water is made up of 2 atoms of hydrogen and 1 atom of oxygen, how do you reckon it splits? It makes 1 OH minus ion, and it makes 1 hydrogen ion. Okay, and the hydrogen is what makes something acidic. So the more hydrogen ions there are, the more acidic something is. Okay, like I said there, more hydrogen ions there are, the stronger the acid is. And just to recap, that acids and alkali are made from water splitting, where the water, because it's H2O, yeah, like there, the OH go together and make an OH minus ion, otherwise known as a hydroxide ion, and the hydrogen left over makes up the hydrogen ion. And that makes something acidic. Okay, and the more hydrogen ions there are, the more corrosive it can be, which means it can burn you. Okay, so what do we know about acids? Acids are substances which have a lower pH than 7. Remember, the pH scale goes from 1 to 14, or 0 to 14, and it turns a litmus paper red. I'll learn more about this later on. Okay, so hydrochloric acid is a strong acid. Ethanoic acid, like vinegar, is a weak acid. Okay, you've got other acids as well, like citric acid. That's found in fruits. Okay, and so these are everyday ions, everyday acids like citric acid and ascorbic acid, which is vitamin C. But you've got the laboratory acids as well, like hydrochloric acid, sulfuric acid, nitric acid. Okay. So OH minus ions, these make something alkali. The more OH minus ions there are, the stronger the alkali would be. Alkalis are often found in cleaning products, okay, and they cause a lot of damage and are said to be caustic, okay, which is, you thought acids were dangerous, well, alkalis are just as dangerous if they're really strong. Okay, and these are everyday ones, so your toothpaste, believe it or not, your soap, your fairy liquid, they are all alkalis. And those are everyday alkalis over here, and these are laboratory alkalis, which is sodium hydroxide. Remember the hydroxide bit, which is right there, yeah? And ammonium hydroxide. So if it's got hydroxide, you know it's an alkali. You know it's an acid because it says acid. Easy peasy. Okay, and those are all the ones that have a pH above 7. They turn litmus paper blue, and they can neutralize, which means cancel out the acids, and they're made of OH minus ions. Sodium hydroxide is a strong alkaline, and ammonia is a weak alkaline, which is why we've been studying ammonia, because it leads to that, yeah. Okay, so what's the difference between an alkali and a base? Yeah, because people think they're the same thing. They're not. All alkalis are bases, okay? They absorb hydrogen ions, which means that they cancel out acids, okay? Now, when bases are dissolved in water, we can call them alkalis. Okay, can you see? I don't know why I'm pointing to my screen because you can't see that. But can you see this? This is an alkali. Okay, because it's dissolved in water. Okay, if it was just a solid, okay, it would be called a base. Okay, so bases, all bases react with acids. Okay, but all the liquid ones are called alkalis. The solid ones are just called bases. Does that make sense? Yeah. So all of the alkalis are called bases, but the ones that dissolve in water are actually called alkalis. Yeah. So anything that reacts with an acid that has hydroxide ions is called a base, but the ones that dissolve in water are called soluble bases. Yeah, alkalis. Okay, copper oxide is an example of a base. Which is, remember, the opposite of an acid is a base. Alkalis are bases that dissolve in water. Go back and have a look at this. This is copper oxide. This is a base. Okay, it's not dissolved in water. Okay, so it's a base. But if I had the liquid form of it, it would be an alkali because it's a base that is dissolved in water. Confused? Yeah, I thought you might be. Just go back through the video and have another look. Okay, so indicators, just like car indicators. When you're in a car, you go left, you turn the left indicator on. Go right, you turn the right indicator on. And they tell you if something is an acid or an alkali. Now, indicators change colour based on how many OH minus ions there are or how many hydrogen ions there are. Okay, does anybody know what scale it makes? It makes the pH scale. Okay, now, litmus is an indicator, but it only tells you if something is acid or alkali. It doesn't tell you how strong an acid or how strong an alkali something is. But you need to know that litmus turns red in an acid. Okay, this is litmus paper, and it turns blue in an alkali. Yeah, can you see that? That is litmus. Red in an acid, blue in an alkali. But it only turns those two colours. No good, huh? Okay, we need something that can turn lots of different colours to tell us exactly what pH something is. And universal indicators can do that. Let's have a very, very quick look at this. This is pH water, and it is at 7. Next item, stomach acid. What pH? Have a quick guess. Yeah, number 2. Another one is water. Seawater is at 8. Lemon juice is around about 4. Oh, 2.4. And unpolluted rain, I'm going to say 5.6. 5.5, it's close. Blood, I'm going to say 7.8. 7.4, damn it. Indigestion tablets, I'm going to say pH 10. 9, I was close. Acid rain, I'm going to say 4.5. 3.5, damn it. I'm going to say car battery acid, I'm going to say pH 1. Yes. Vinegar, I'm going to say pH 3. Yes. Milk, I'm going to say 5.5. Damn it. 6.6, because we're very weak acid. So all of these, when it's pH 7, it's neutral. When it's 4, 5, it's very close to neutral, but it's below 7, so it's still acidic. And all of the 0, 1, 2, 3 is a strong acid. And if it's 13, 14, it's a very strong alkali. But if it's 8, 9, it's very weak alkali because it's close to neutral. Does that make sense? Have a go through my explanation again. Okay, next item. Cola drink, I'm going to say pH 3. 2.8, close enough. And caustic soda, I'm going to say 14. Yeah. Okay, next item. God, this is going on forever. Household cleaner, 12. 11. There you go. Okay, so just make sure that you're all aware of the different pHs of different things. Okay, now, we're not going to do this, but this is the pH scale over here. So you describe this, this will be a weak acid. Okay, this will be a pH 1, so it'll be a strong acid. pH 8, that'll be a weak alkaline. 10, it will be a weakish alkaline. Stomach acid will be a strong acid. 14 will be a strong alkaline. pH 4 will be a weak acid. Okay, that's what you need to know. Okay, yeah, and it makes a pH scale. Yeah, we've been through that. We're happy with that. You may need to match up the colours to what pH it needs to be, but you guys can do that, no problem. Okay, so certain plants only grow in certain soils, and so actually the geranium plants grow one colour in an acid and actually go another colour in an alkali. So farmers, or gardeners really, need to know what pH their soil is, so they might test it, but they might put, if it's too acidic, they might put an alkali on it to make it more alkaline and have a different colour geranium. Interesting, huh? I'm not going to do that. I'm going to skip past this. Okay, making salts. Now, an acid and an alkali will neutralize each other. and that will make a salt. Okay, so an acid and a base gives you a salt. Okay, and you need to know the name of the salt, what happens when different acids and different alkalis react together and make the different ones. Okay, so the first part of the salt's name comes from the base. Okay, so sodium hydroxide, we know that the salt is going to be sodium. So this is the base that we're looking at over here. And whatever the first part of the name of the salt is going to be, the first part of it is going to come from the base. So we know sodium hydroxide, which is the base of the alkali, the first part of the name is going to be sodium. The second part is going to come from the acid. So we know this is sulfuric, so we know it's going to be sulfate. So the name of the salt is going to be sodium sulfate. Yeah? And that is that. Okay? I'll rush through that very quickly. Pause the video and have a read of the slide, please, for me, guys. Very important. So, as I said, shall I run through that again? Yeah, first part of the salt's name comes from the base. So if you're using the alkali is sodium hydroxide, you know that the first part of the name of the salt is going to be sodium. Second part of the salt's name is going to come from the acid. So if you use sulfuric acid, it makes sulfate. Okay, now there are rules with this. Okay, so I think I'm going to go through this actually. So the first part of the salt's name comes from the base, doesn't it? So you know that the first part of this salt's name is going to be calcium. You know that the acid is called hydrochloric acid, so you know it's going to make a chloride. So I know that the name of the salt is going to be calcium chloride. Where's calcium chloride? Here we go. So that is calcium chloride. Okay, guys, pause this and have a go before I go through the rest of the video so you know. Okay, right, now, magnesium oxide. So I know the first part of the name is going to be magnesium, and I know the acid is nitrate, so that's going to make a nitrate. Okay, so I'm looking for magnesium nitrate. There we go, magnesium nitrate. Okay, copper oxide and sulfuric acid. So I know the first part is copper, and I know the second part is a sulfate because it's a sulfuric acid. So it should be copper sulfate, and it is copper sulfate. Okay, ammonia and nitrate. Now, ammonia is a bit of a funny one because it makes ammonium. Okay, anytime you see ammonia, it makes ammonium. And I know this is nitrate, nitric acid, so it makes a nitrate. So I'm looking for ammonium nitrate. And there we go, ammonium nitrate. There we go. Potassium hydroxide, sulfuric acid. So I know the first part of the name is going to be potassium. Second part is going to be sulfate. So potassium sulfate. Now, they're not going to give it as nicely easy peasy as this because I've got my bases and my acids all in one nice row. So they might mix it up a little bit. So they might say, what salt is made when sulfuric acid reacts with copper oxide? And so you're going to know that the end bit comes from the acid, so you know it's going to be a sulfate, and you know that the first part of the metal, okay, that you get, because these are all metals, aren't they? Calcium, magnesium, copper, not that one, and potassium. Yeah? Easy peasy. Let's go through this one. Colours from the fireworks are made from when certain salts make, so calcium chloride always makes a bright red colour. Table salt, sodium chloride. Indigestion remedies always contain magnesium, and there we go, that's it, that's all we need to know. So when an acid and alkali react, it makes salt and water, don't forget that. Okay, so again with this, hydrochloric acid plus sodium hydroxide, what is the salt going to be called? I know it's going to begin with sodium because that is the name of my alkali, and the metal from the alkali is sodium, so I know it's going to be hydrochloric acid, so I know it's going to end with chloride, so it makes sodium chloride. Yeah, the sodium from the alkali, which goes right there, okay, and the chloric, yeah, hydrochloric, and the chloride is going to make the chloride bit right there, okay, making sodium chloride. Happy days, okay, and there we go, and it neutralizes it, and so what happens is it makes a salt and water. Acid and alkali makes salt and water. Okay, right, fertilizers and crop yields. Why do we add fertilizers to crops? Well, we need to give them fixed nitrogen so they can make protein for growth and repair. Okay, because remember what I said, that plants need nitrogen to make protein. Okay, that's why we give fertilizers to crops. Is nitrogen the only element they need? No! They also need, we need vitamins and minerals to be healthy, don't they? We need vitamin C, calcium, that's what makes humans healthy. But plants also need their minerals to be healthy, and they need phosphorus, okay? They need potassium, and they need the nitrates as well. Sorry, I drew a blank there. They need nitrates as well, Okay, and so what you get is you get fertilizers called NPK fertilizers. Okay, now fertilizers. So the N stands for the nitrogen, actually stands for nitrates. The P stands for the phosphorus. Okay, which is right there, and the K is potassium. Okay, and that's why they're called NPK fertilizers. So key elements in that. What key? So this is the fertilizer. This is potassium nitrate, and so this is the potassium, and this is the nitrate right there. Okay. So why don't we just keep adding loads of fertilizers? Isn't this a problem? Okay. Indicator species. I haven't gone over indicator species. That's a good point. Okay. Basically what happened is that the farmer. Can you see all this green stuff on this lake? Okay. This is because the lake has been getting lots of fertilizer, and all this algae has grown over the top of it. Why is this a problem? Well, what happens is when farmers live near lakes, they put loads of NPK fertilizer on it to make their crops grow as fast as they can. But what happens is that the fertilizer runs through the soil into the water, and that makes the algae grow on the top of the water. Now, what happens is all the plants below the surface, by the way, this is called eutrophication, and all the plants below the surface, because it's really dark, as you can see that, imagine there's no sunlight getting on the underneath of that. So all the plants underneath would start dying. Okay, now as they die, the microorganisms are going to eat all the dying plants, but as the microorganisms eat all the dying plants, they use up all the oxygen in the water. So there's no more oxygen in the water, and when there's no oxygen in the water, fish die. I shouldn't say that so gleefully. It's very sad that the fish are dying. And so there you go. Describe and explain. I think I'm going to miss that out. Uses of salt. Okay, use of salt. Salt is used as a preservative. 1 second.